I'm Kenzie. I'm the UK sales manager for 2G. We're a German company. We're a weird company as well. Effectively, we're a company of nerds. We really are. Even our CEO is a nerd. So our CEO started the company 28 years ago in his garage. And then obviously since then it's developed. We're a weird company as well because, I've been in the power generation game for 25, 26 years. Until I started working for the company, I'd never even heard of them. And it's 2 miles down the road from my house. The weird thing is that we're the third biggest builder of stationary gas engines in the whole of Europe. And no one has a clue who we are. And the reason being is, as I said, there's 850 of us work worldwide. 92 are in research and development on the engines. We have one in marketing. So we're brilliant at designing things, we're great at building engines, no one's heard about us. And it's even fact to this, when I first joined 6 years ago, as soon as I got into the company, I found out we had the world's first hydrogen engines running. And I said to the Germans, why haven't you actually told anybody about this? And they said, do you think we should? Because they thought it was a bit like boasting. And it was sort of going against their mentality that you build the world's first things and you should go and tell people. And they thought, we build the world's first and we'll tell nobody because we don't like the idea that we're boasting to people about it. We're also slightly weird as well that we build half the engines, well, the engines for half our competitors. We just paint them all different colours inside the factory. So we build all the engines for Centrica, we build the Rolls-Royce 500 series engines. So, normally when we tell people we build Rolls-Royce engines, it tells you the sort of pedigree that we actually have, obviously, for designing and building engines. So, it is strange. So, if you ever go to the factory in Germany, in Heek, and pretty much we've taken over the entire trade in the States, you can just see the engines being painted different colours and different nameplates being put in them in the manufacturing point, depending, obviously, who we're selling to. So, it is one of those strange and weird ones that I said our competitors are also selling our engines against us in the market, just in a different colour. So, anyway, we're a bit strange. So we basically develop and design gas engines. In reality, it doesn't really matter what type of gas it is. For us, gas is gas. So hydrogen, syngas, natural gas, biogas, any type of gas, we build engines obviously to fit that. And the great fact is that because we've got such a large research and engineering department, if we come along and we go, we want the engine to do this, they make the engine that does that. And it's the same way, obviously, for the development of the engines and the different gas structures and everything else. We've got people who just work on this day in, day out. They just breathe the engine technology. So easy for them. So we're always ahead of the game for obviously engine design and engine development. And because we're a relatively small company, and because I said we've got a CEO who's an engineer, we don't really worry too much about, do you think we have to develop a market plan for where this is going? Research and development build engines sometimes, and later on go, we haven't got the application for that, and they just build it for something else. So it's a great company to work for, but once again, nobody's got a clue who we are. The hydrogen engines, we're not ever saying that this is like the be-all and end-all, that you've got to build a hydrogen engine and that's going to be solving every single bit of the carbon infrastructure or the carbon problems you have. It just fits into a part of the overall strategy. Building out PV nowadays is just so cheap. And now obviously onshore wind is obviously going to get further along now with the planning applications are being dropped. We just see hydrogen fitting in as a part of the overall mix. And especially with the excess surplus of electricity, especially from wind farms at night, using that surplus electricity to generate hydrogen is obviously a way forward, rather than obviously trying to think, we've got to build plants just to manufacture hydrogen, and that's obviously the be-all mechanics and economics of doing it. A lot of the projects we do over in Germany, they effectively use the electrolyzers to do grid balancing. So 30% of all the wind turbines in the world have got to turn out the wind at night because obviously they can still generate power, but there's obviously no demand for it. So obviously, rather than obviously paying obviously all the subsidy, I used to work for SSE, so I know about the subsidies that the government pays us to turn the wind turbines out. In Germany, they use electrolyzers to do grid balancing. So rather than turning the wind turbines out, they make hydrogen. So a lot of the projects we work on, we make hydrogen all throughout the night, and then we utilise it during the day. So it's just a way of actually, it's an energy vector, an energy storage medium. So rather than employing big batteries and all the rest of it, use the excess surplus energy you've got at night to make hydrogen. That's it. And then the economics just change on the head. Rather than thinking, we're building this plant just to generate hydrogen. Well, the economics won't work at the moment. But you're thinking, we're building this to use surplus electricity. So effectively, the energy input is zero cost because they're effectively turning the wind turbine out the wind. So obviously, if you turn it out the wind, it's got no value. so utilise it. It's also quite strange in Germany.
Because in effect you're competing with a battery, aren't you? That you're taking electricity, turning it into hydrogen, which costs capital and has efficiency losses and all that sort of stuff.
Yep.
Taking that hydrogen, turning it into heat or whatever. Why not just stick the electricity in a battery and store it?
Well, you can do that, but once again, obviously, the duration of energy storage on a battery is also, once again, one of those different things. I mean, people like Conrad, energy storage, obviously store all that, that's moving to batteries now more than engines, obviously because of the efficiencies and the cost of it. But in Germany, especially the project we work on down in Bavaria, in Germany, you're allowed to sell hydrogen back onto the gas grid. So they sell a lot of their hydrogen to Greenpeace. So Greenpeace buy what they call wind gas. So that's where the economics of generating hydrogen comes from. So that's why, I mean, I've got the case studies, you can see it in a minute. But, so they make hydrogen effectively to sell to Greenpeace. But obviously the byproduct of that, if they've got so much hydrogen, they've also got natural gas engines. So if they haven't sold all of the hydrogen to Greenpeace, they use the hydrogen into the engines. But the great thing about the engines as well is, because obviously the design of it and everything else, we can do gas blending. We can actually run the engines on 100% hydrogen, 100% natural gas, or effectively any blend of the gases in between. So that's where the economics of it comes from. So rather than storing electricity, which is obviously, you know, well, that's what I'm saying. Yeah. I mean, everything's weird depending, obviously, what the regional, obviously, subsidies and everything else is. And obviously, the municipalities in Germany are built so they're effectively their own, like, you know, energy supply companies, all the little villages and everything else. But down in Bavaria, they specifically target selling hydrogen to Greenpeace. So it is, I mean, it's like everything. I mean, the last slides on this presentation are all about the economics. It is just, a lot of times, economic. Cost is driven by money. So generally, obviously, in most standard engines, we obviously use gas mixers. So obviously, we have a gas mix where we do obviously the formulation or the mixing, obviously the gas in the air before we put it through the turbochargers. And the turbocharger obviously then feeds that gas mixture obviously into the engines. This is pretty much, apart from the non-aspirated engines, that's pretty much how all engines work. For us, when we design engines, once again, most of it is just I mean, the basic core engine's effectively the same, depending obviously with gas and everything else that we're using. It's really just messing around and playing around with the compression ratios and the timing, and when we're doing the injection and when we're doing obviously the spark effectively into the gas mixture. So we're normally used, obviously in between obviously playing with biogases and natural gas, and obviously conversely obviously into hydrogen. It's just effectively getting that compression ratio right and the compression and the timing. But also as well, we don't have flat cylinder heads. We have rounded cylinder heads, and we spent an awful lot of time, the research and development team, obviously designing the cylinder heads. So obviously the compression ball is exact. So this is why the efficiencies of the engines are so high. We spend an awful lot of time playing around with this. It's like a lot of people will say, oh, you'll have flat heads. We don't. It's a slightly curved head, obviously, for that. But this is the thing, I said, for us, it's just a case of, we have the engines on the test cells. We've got the engines on the test cells, and we've got the engineers who know how to design and how to build them. So every time we just need a different gas or a different structure, depending on the methane, or depending obviously how much methane's in the biogas, we just play around actually with the compressions and the timing ratios of it. And effectively, that's all it is. The actual core frame of the engine is exactly the same for all gas types, all gas structures. Hydrogen is slightly weird, and it's got bad points and it's also got an awful lot of great points. But in reality, our entire development of these hydrogen engines wasn't designed for hydrogen. Originally, we were designing syngas engines, and we were designing a lot of syngas, obviously the syngas structures that had more than 50% hydrogen, obviously contained obviously within the syngas. The problem with hydrogen is it's got a low detonation temperature, a lower also ignition temperature, and obviously compares to natural gas and obviously propane, which is just shown for a reference point. So every time obviously we're moving a gas mixture through a turbocharger, sometimes obviously the turbochargers run at a couple of 100 degrees centigrade. So when you're moving generally more than about 40-50% hydrogen through a turbocharger, you're getting pretty close to the auto ignition point of hydrogen. So originally, everything that we designed for syngas, or for these hydrogen engines, was based on the syngas. So what we found is as soon as we were moving more than 40-50% hydrogen through the turbocharger, we would run the risk of blowing the turbochargers up because of the lower detonation temperature. So originally, so once again, we designed it for the syngas. We, rather than pitting the gas mixture and everything else to do the conventional way, we actually don't put the hydrogen, or we didn't put the syngas through the turbo, through the gas mixing valve. We were still turbocharging the air, but we weren't putting the gas into it. And then all we were doing later on is we were putting an injection valve onto the engine, and we were injecting the hydrogen or the syngas mixture back into the turbocharged air just in front of the cylinder head. So I said we'd originally developed all of this for syngas, or for these 50% concentrations of syngas. Then 12 years ago, something like that, is it that slide? So that's all we actually do to the engine, it's just that injector valve. So about 12 years ago, the German government, they were umming and ahhing whether to go for the hydrogen economy or whether to back the battery economy. So they wanted a demonstration project to prove that the concept of generating hydrogen, obviously from wind farms, low pressure, low temperature storage on site, the injection back onto the hydrogen injection back onto the gas grid. They wanted a project doing to prove that all that sort of technology could work together. So obviously they came to us and asked us if we could design a 100% hydrogen engine. And in reality, all we did is we took the syngas engine from running from 50% hydrogen, we played around with the compression and the timing, and we just made it run on 100% hydrogen. In reality, it didn't take us that long to do. It was just a case of retuning and playing around with the compression and the timing of it. And in essence, that's the only thing that we add to an engine, an injector valve. Because once again, instead of the turbocharger, we just bypass it. We don't do anything else. When we were originally doing our third series of engines, we also used to have to change the cylinder liner and the piston head, just so we didn't suffer from hydrogen embrittlement on the materials. When we moved to our fourth series of engine, which we moved to a couple of years ago, our CEO made the decision, because we know effectively, because the engine's lasting 15 years, 15, 20 years, we know all the engines, all natural gas engines, at some point over that life, are going to be running on hydrogen. There's just no other way around it. So now every single engine we have the cylinder line in the piston head with that hydrogen materials already specified on it. So now the only bit we actually have to add is that gas injector valve. And so if we effectively can modify any single engine that we've got in the fleet to run with 100% hydrogen. Adding that valve takes about a week on site. There's obviously one valve per cylinder, but that's all it is. That's all we do to make an engine run on hydrogen. And I said it's nothing new, it's nothing weird and wacky. As I said, when we've done all the presentations for this with all the major consultancies 5-6 years ago, they all go, "Is that it? Is that what you've done?" Because they think we've developed some sort of new technology or anything. It's a bog standard natural gas engine with an injector valve. And I said we just play around with actually how the hydrogen actually gets into the valve. And it really is that simple. It's not difficult to make an engine run on hydrogen. I said for us as a company, it's gas. We build gas engines. And hydrogen's got an awful lot of good properties compared to natural gas. I mean, some of the syngases and the biogases that we have to deal with are just horrendous on the engine. Hydrogen's so clean. It's a perfect fuel for an engine. So this was the original, I mean, this is the actual project. This is the actual engine that's actually in Berlin Airport. And as you can see, at that point, we didn't even bother taking the gas mixer off. All the hydrogen engines we sell now that are dedicated hydrogen engines, we don't bother putting the gas mixer on. But when we did the demonstration project for Berlin Airport, we still left the gas mixer on it. So obviously, if we put the injection rail on it, we put the gas mixer, so that engine would run dual fuel. It would run on any combination of gases. But once again, the gas mixer is never used because it's a purely and utterly a hydrogen engine. But obviously, all the dedicated hydrogen engines now obviously don't have obviously that gas mixer on it. But obviously, it's just a weird thing. So the big advantage of this is, as I heard, we can make every single one of our engines run on hydrogen, 100% hydrogen. Because people think, well, you've got to take the engine out, it'll be a new block, it'll be this. No, you have the hydrogen rail on it, that's it. So once again, people aren't buying assets that will be dead if we do transition to a hydrogen economy or a gas network with hydrogen in it. You get an engine that can, I mean, the bog standard engine, I said, it's only because of the issue with the turbocharger and the 40% blending that we start adding the gas injectors. The normal gas engines, the natural gas engines, straight out the factory without doing anything to them, will take 40% hydrogen, doing nothing to the engine at all. You could run a blend of 40% hydrogen into it, the engine doesn't care. I said it's only the turbocharger that has the problems, obviously, with the higher concentrations of hydrogen. So the idea that we're only going to get the gas grid that's going to get potentially 20% hydrogen in it, not an issue at all. One of the other things that we did as well, we designed as a company several years ago, We originally, because obviously the gas grid in the UK, it's normally got obviously a methane content of over 80. The only issue when you start blending hydrogen into natural gas, you lower the methane number of the actual gas. So you start dropping it down. When you're at a 40% concentration, you're basically down to about 70, 72% methane content compared to 80% as normal natural gas. So we took a decision a couple of years ago as the company, every single one of our engines are tuned to methane 70. So the lowering of the methane number by blending 20, 40% hydrogen into it won't cause us a problem at all. Once they start, for all our competitors' engines, which are tuned to 80 methane, if we start getting into that hydrogen injection onto the gas grid, it'll start lowering the methane number, the engines will start knocking, because they'll get early detonation on the cylinders. So the first thing they're going to have to do is start deracing all their engines. For us, we don't care. We made the decisions years ago to get ready for hydrogen. So we've got the hydrogen embrittlement materials already specified. We've got the engines tuned to run at 70 methane. I mean, once again, I said, we made this, because obviously tuning an engine to 70 methane compared to 80, you lower the efficiency very, very slightly. So people said, well, why are you doing that? Because you're going to look worse compared to your competitors. But the stuff's there for 15 years. We're selling something to somebody that's going to run no matter what you do to it. So once again, I said, we were clear on our vision that hydrogen is the future. So we weren't just thinking, right, let's try and convince people to buy this engine now and argue that it's 1 or 2% extra efficiency compared to everybody else. The engines were so efficient anyway, us lowering the 1 or 2% of the efficiency anyway, we were still more efficient than anybody else in the market anyway. But we took that decision just to make sure we were ready for the hydrogen in any sorts of blends. And obviously, because we sell engines all over the world, I mean, the UK is now getting way behind compared to everybody else. Our biggest market for hydrogen engines is Japan. And the Japanese gas grid's already 40% hydrogen. So us at the moment, 0.1% or less, we're way behind. So Hong Kong's 40%, large parts of China 40%. Obviously Germany's getting obviously into the higher percentages now. So that's why we just don't build engines for our UK market, we build engines for our worldwide fleets. And once again, I said a lot of those are on the 40% hydrogen already anyway in the gas grids. But once again, the engine's there for it. And once again, obviously, one of the issues obviously with hydrogen is obviously the energy density of it. Obviously, it's only 3 times the energy density compared to natural gas. So obviously, we're shoving an awful lot more gas through the engine than we would through natural gas. So once again, we run at higher pressures. So normally, on the natural gas engine, we're only running at a couple of 100 millibar. When we're running hydrogen, we're running at 4 bar. So obviously, we shove hydrogen through that engine quickly. And once again, I said, it's all development work we've done already. So everyone now is playing catch up with us. But once again, we're open about all of this because I said we have a team of nerds who just design all these things constantly. But once again, I said that hydrogen hasn't got, or it's got some issues of it compared to obviously other things we're working, and obviously energy density is one of them. One of the great things about hydrogen though is its combustibility. So normally natural gas and everything else, normally we work obviously on operational windows. So there's a lot of gases, you have to mix obviously air with them to obviously get the gas to combust. But there's a limit between how much air you can actually inject into a gas and still get an igniting, obviously within obviously a spark plug, which is obviously called the control window. So those control windows is obviously where the amount of air you can mix with the gas and still have combust. With hydrogen, it's massive. So obviously hydrogen has just got an absolute ginormous control window. So we can mix an awful lot of air in hydrogen and make it go bang still in the cylinder. The reason this is really, really handy, when we first did the engine at Berlin Airport, we based it on the German biogas specification. Because when we designed an engine 12 years ago, we thought, what specifications should we pick? So they chose the German biogas specifications, which was 500 NOx. Since then, we obviously know a lot of these engines now, because of the corporate world and they're going green, a lot of these are going to go into city centres. So the engine now, all run at 95 NOx. And we did nothing to the engine except increase the lambda value. So what we did is shove more air into the hydrogen, and we still have it go bang, but by increasing the control window, increasing the airflow ratio of the gas, we lowered the NOx from 500 NOx to 95. With no change of efficiencies or power output of the engine at all whatsoever. We know we can go even lower. Because at the moment, I said we're running about 3.4 on the lambda value. We know we can get down to 5 or 6. The problem is when we start hitting these numbers here, we do then start eating into the power outputs of the engine. But we know we can actually run the engines down to 30 NOx. The reason we chose 95 milligrams NOx is the Clean Air Act in pretty much every city centre in the world. So we chose a limit that complied with the Clean Air Act. But once again, if people say, well, we need it even lower, I mean, some of the councils in London go, well, we want 50 NOx. Well, great, you can have 50 NOx, we'll just increase them, but it'll then start eating into your power output a bit. But we don't have to put SCRs or anything fancy on the exhaust, hit those NOx levels. We just play around with the lambda values. But once again, everything's possible. Everybody can have anything you want, and that's why hydrogen's got a lot of great advantages. And I said lower emissions, because why would you choose a carbon zero gas that has high NOx emissions? It makes no sense. So that's why I said now all of them. So the MCPD, the Medium Plant Combustion Directive, is still 250 NOx. We're running at 95. We don't have to, but we specifically do it because I said if you're going for a green solution, why not have a green solution that's also got a green nitrous oxide limit as well? So I said, for us, hydrogen's wonderful as a fuel. And so once again, I mean, we've got these, our entire range, all of them we have running on hydrogen, so our 4-cylinder all the way up to our 20-cylinder. We've also recently just launched our 16-cylinder as well, that fits in the middle of that. But the efficiencies and everything else, they're all the same as they are on natural gas. The only thing at the moment on the efficiencies, well, not the actual efficiencies, but the power outputs. At the moment, because we've only got 26 hydrogen projects working all over the world. So at the moment, when we're running engines on 100% hydrogen, we derate the engine 25%. The reason we're doing it specifically is hydrogen's got no knock resistance, so it's easy to obviously get early detonation temperature, early detonation if you get the combustion and compression ratios wrong in the engine. Because we've only got 26 projects working all over the world, we want to make sure there's no issues on those engines at all. So we derate the engine 25%. So that's why, I mean, when on our 420, which is our 20-cylinder engine, when we run that on natural gas, we run that at 1 megawatt. But we specifically made this decision because at the moment, up until the next couple of months, when we're doing the testings of the engines, we're still using bottled hydrogen in the factory. So we haven't got the engines on test 24 hours a day. But we're going to be on that, the hydrogen backbone that's obviously going through Germany. Our factory's going to connect it to it. So as soon as our factory's on it, we're going to get the engines on test 24 hours a day on the hydrogen. We've actually run the hydrogen engines at a higher electrical output than we have on natural gas. So we know it's all possible. But we haven't got those long duration tests to obviously prove it, and the compressions and everything else. But Frank, who's the head of our R&D, he said it's not a problem at all. But from a sort of media point of view, I said we take that slight de-risk or that slight derate on the engine just so the engine runs completely sweet. Because the worst thing we want is one engine to be running slightly wrong, then people go, oh look, hydrogen doesn't work. It's all a complete load of nonsense. But compared to our competitors, I mean, I said like MTU and Yambacher, they're derating their engines 30 and 40% on hydrogen, because they're even more risk averse than us at the moment. But I said in the next couple of years, as soon as we're on that pipe and as soon as we've got the engines on test, we'll just reach in all the engines all straight back to the same power output, same power on natural gas, same power on hydrogen. It's completely possible. And I said in the test cells, we've had the hydrogen engines actually running better efficiencies and better power outputs.
What do people do with the heat? Is that a bit of a cheat, saying you get half of the engine? No. I'll show you one of the examples. I mean, because this is what we build. We're a CHP company, combined heat and power. So obviously we do what we class in. Low grade, it's 100 degrees. It's
90, but no, well, it depends. Standard temperatures, we didn't do 90 degrees, but we can do absorption cooling, which we did on the project in Dubai, which I've got a slide on in a minute. We can pull steam off if you use the exhaust gases only. I mean, when we do, as a company, if we're targeting industries, the best industries to work in is the food industry, because they have high steam demand, high low temperature water demand, obviously for washdowns and everything else, high electrical demand, and generally they run 24 hours a day. So for us as a company, food manufacturing is the best.
Going back to comparing it to a battery, you you get 96% of your energy back is electricity rather than...
Yeah. But a lot of people need the heat more than anything else. I mean, probably the best examples ever for a CHP where the actual thermal load is higher than the electrical load of swimming pools. Pretty much every single council swimming pool's got a CHP in it. Every hospital has got a CHP. Every university's got a CHP. Anybody's got high thermal base loads or high heat loads, like swimming pools, hospitals, those types. Yeah, absolutely. Well, we did the world's first district heating, you'll see that in a minute as well. But yeah, everything has got high heat load, high electrical load. I mean, the cash is all in electricity. That's where all the economics, the cash is in electricity. The heat's the nice to have. But the nice to have is free heat. And I said things like things like the hospitals and everything else, their thermal load is miles higher than electrical load.
I'm a bit old school, you see. I think from the days of healthy steam, it's worth nothing. You just throw it away.
Yeah, no.
I guess if you're integrating it with domestic or industrial stuff, it's worth it.
Yeah, well, let's say we generally just do a lot of the industrial stuff. Because once again, it's like cash is king, so everything comes down to obviously economics at the end of the day. So, I mean, this is why they generally don't work in office buildings, because you're on like 1,800 hours a year. If you're on a hospital, you're on 8,200 hours, 24-hour manufacturing, 8,200. So those, we target 24-hour operations, but food manufacturing, because obviously they get used an awful lot of water for washdowns. Yeah, but as I say, through the engines, we say we can produce anything: steam, low temperature, high temperature. Obviously, if we're going on high temperature, you go into pressurized systems. But yeah, I mean, heat's not a problem. I mean, obviously, 50% of the heat that comes off the engines, the exhaust gases. So obviously, from those, we can do anything we want. Obviously, steam and everything else. But obviously, if we're in a standard low temperature hot water system where we couple all the three heat exchangers together, yeah, we generally pull it out at 90 degrees. But yeah, so it's not a fiddle. We do use an awful lot of the heat. But this is obviously this is the actual engine out of the test cells, which you can see obviously why the engine looks a complete mess in the test cells. But obviously the efficiencies and everything else between natural gas and hydrogen, there's basically negligible difference at all. So once again, I said, we spend an awful lot of time doing this sort of like research and testing and everything else. And obviously we have a lot of the universities come down and witness obviously all the testing, because pretty much we're the only people that go running the engines. So obviously a lot of the universities in Germany have got obviously high interests in everything obviously that we're doing. But yeah, so I said for us, I said hydrogen's just wonderful as a gas. So these are some of the projects. So obviously I've got the case studies of most of these. So obviously the Total one, it was the hydrogen project we did in Berlin Airport. That was the first one. Apex is an energy centre down in Rostock. HAPSA is municipal works. That's the one where they do obviously all the selling of the hydrogen gas back to Greenpeace and everything else. Eslington was available. I said most of these, I've got the case studies in a minute. Kirkwall Airport was the first one in the UK. That's got the ICM electrolyser on E-Day. And Toyota have got them in the main manufacturing sites over in Japan. I mean, the most interesting one that we've done recently is over in Taiwan, on one of the semiconductor factories. The byproduct of the semiconductor factories, they're reprocessing, and the reprocessing of the waste produces 99% purity hydrogen. So it goes straight into our engines, and the case study on that is fantastic. And there's a lot of people watching that now. But yeah, so we've got them everywhere. I said this isn't something that we've got on the whiteboard. They were saying, well, this is what we're going to do on the future. This is what could be done. We take people to see these. And the crazy one is, I said, the one in the UK, which is Kirkwall, it's actually always quicker. We take everybody to see Apex over in Germany, because it's actually quicker to fly into Germany than it is to get to Kirkwall Airport. I keep trying to convince people to come and see the one over in Dubai, but so far no one's taking me up on that. But the one in Dubai works absolutely sweetly. I've seen the one in Germany, God knows how many times. But I must admit, the gin distillery up in Orkney is fantastic. It's just an absolute pain to get up there. So this was the first one that we did. I said this is the German government project, which we did with Total. And I said it was effectively just to demonstrate everything, obviously for the wind farms, through the electrolyzers. They obviously, all of the vehicles on the airport were obviously hydrogen fuel cells. It was to test obviously the hydrogen injection back onto it, low pressure, low temperature, hydrogen storage. It was a complete joining of stuff together just to prove it could all work together. And obviously we just did a little bit, which was obviously the first engine in the middle of it. But it was, I said it was a nice project. But Berlin Airport's also quite a funny story if you want to go kicking the Germans, because they always pride themselves on their engineering prowess and everything else. The airport's not built so you can land the runway's not built so you can land planes on it. So the airport hasn't opened. So if you ever know Germans, ask them, why haven't you landed planes at Berlin Airport? They go, so yeah, they were great at building all of that. They're great at building the structure. They got a load of idiots in to build the runway, so you can't land planes on it. But there you go. So this is the first engine. So once again, I showed you that before. So I said these are existing projects. I said this ain't what we made up. I said that was we were on our third series of engines. I said we're on the fourth series now, but that was the world's first hydrogen CHP. I said this is the project over in Dubai. It's quite funny as well. A lot of my friends work in Siemens. And this is obviously the board of Siemens. So in the Siemens brochure, you see the main board all the way over here, and there's a sticker there because where they put it over our engine. But obviously that was connected to the world's biggest PV farm. So obviously it's slightly different from the other ones that we work with. So all the ones we have connected to wind farms, we generate hydrogen during the night, we use it during the day. That one generates so much hydrogen during the day, it runs 24 hours a day. But also we have that running on a trigen system. That project was done for the World Expo. So the World Expo also had the Hydrogen Expo next to it. So obviously we provided all of the power for the Hydrogen Expo bit. So obviously it was a project we did in collaboration with Siemens. So obviously that's a 0.5 megawatt engine. So obviously it's Siemens electrolyzers and everything else on it. But that was a great project. But once again, it was purely and utterly to demonstrate that all this technology can work together. Because obviously the Middle East at the moment are going mad for hydrogen. Because obviously they can see there's going to be an end at some point, obviously, to the oil industry. Whether it's 20, 30 years, whatever, but they've got an entire industry set up for transporting gases around the world. I mean, it'll be converted into ammonia, because obviously it's easier to sip ammonia, obviously because of the energy density. But at the moment, obviously, they're covering the deserts in PV, and that's all you need. You just need renewable power, PV, wind, water. You can make hydrogen. It's like, obviously, Morocco and those type of places, they're going mad, obviously, for hydrogen generation. And Australia, effectively, is going to be covered completely with PV. They're going to sell all their hydrogen into Japan. So it's changing the economics, because there's a place like Morocco, they've got no natural resources. They've got sunshine, they've got water, and they make 8 miles from Spain. It makes sense. You can all of a sudden become a power in the world industry by having no natural resources. So obviously, once again, I said that was just, the simple overview. I said this is the only hydrogen engine that we've got that actually runs tri-generation. So obviously, we've got an absorption cooler on it because the last thing that they needed over in Dubai was more heat. But obviously, having cooling was quite handy. So obviously, we put an absorption cooler on it. So we produce electricity and we produce cooling. If you don't know how absorption coolers work, that'll give you a headache on how you can produce heat out of cooling out of heat. But I'll give you a headache a different time. So this is the project down in Bavaria. This is the Hapsford Energy Centre. This is the one that sells the green gas and hydrogen. Once again, it's another Siemens electrolyser. So once again, because obviously we'd already had the natural gas engines on there already. And so obviously the natural gas engine obviously filled the school, the swimming pools, all those types of things. And so obviously decided, well, we've got all this wind power because the way the municipalities work in Germany, their own little energy companies. So like we have the DNOs and everything else in Germany, you have hundreds of them because each region becomes effectively its own DNO. They built out so much onshore wind, they ended up with 200% electricity compared to what they needed, which at night was causing an awful lot of problems. So once again, they put the Siemens electrolyser on purely for grid balancing. But the benefit of doing that is they were generating hydrogen. So they sell it to Greenpeace and they run it through the engine. And then if they either sold all the gas or they haven't produced enough hydrogen, it runs on natural gas. And so that's the great flexibility about the engine. Once you've got those injector valves on it, it'll run on anything, any combination, pure natural gas, pure hydrogen, any combination in the mixed gases in between. The mixed gases is also quite strange because one of the projects we do over in Japan is one of the greenhouses. Well, we can't run the greenhouse engine on 100% hydrogen because the greenhouses want the CO2 for the growing. So we have a dedicated blending valve on it that bleeds exact amounts of natural gas into the hydrogen, because it's the other way around. They have the pure hydrogen and they blend in natural gas rather than having natural gas and blending in hydrogen. They have the pure hydrogen and they blend in a specific amount of natural gas just to produce CO2 out the back end. specifically for the greenhouse. And so it's a strange one, because obviously they use SCR scrubbing, because obviously if you inject hydrogen into carbon dioxide into a greenhouse, you get a 40% bigger yield. So it's a bit of a strange one of the projects. But once again, I said for us, we're happy to play around with engines. This was the world's first hydrogen district heating scheme that we did over in Eslington. This is a university campus. So once again, it feeds obviously all the students' accommodation, obviously all of the office blocks and everything else. And once again, they did it as a demonstration project to prove that you could run district heating schemes on hydrogen. But at the end of the day, I said, I mean, most district heating schemes run on engines anyway. It was nothing different. We just changed the fuel input. And once again, this is how I said, all this idea of district heating schemes being carbon zero. Simple, just change the fuel, whack an injector on the engine, there you go. You've got all the infrastructure already in place. Why bother ripping it all out? Just change the fuel into the engine. I mean, it's the arguments we're on, the discussions we have at the NHS all the time. They've got the engines, because obviously they're getting into the throw. We sell heat pumps, so we're getting into the throws. They're going, oh, we want heat pumps, we want this, that, and the other. I think, oh, why? We're going to have to rip out all of your infrastructure and put a whole load of new infrastructure in. You've got the infrastructure in the engines there already. Just put hydrogen into it. There you go. You haven't got to buy any more equipment. You've got to buy a couple of valves. Just get hydrogen. So I said, well, why buy an entire new project and new infrastructure? Just use what you've got. Just change the gas. It's not hard. I said, there's thousands of these things that exist already anyway. Why throw something away that's working? Just change the gas. The gas is the problem, and the gas is the easy thing to solve. So once again, I said, it's just a complete district heating scheme. Once again, we have some heat pumps on there as well. We designed it that way, obviously from the start. This was obviously the project that we did up in Orkney. We did this as obviously part of the European Marine Energy Centre. This was also the weird one, because this is the only project where the hydrogen's actually delivered to site. So in every other project we've got, we have the electrolyser effectively next door to the hydrogen. We have the electrolyser, we've got a hydrogen storage tank, and obviously that feeds into the engine. The hydrogen for this is actually produced on a different island. So that's got an ITM electrolyser over on E-Day. And the reason it's over there, the interconnector back to Scottish mainland's rubbish. It's owned by SSE. I used to work for them. It's where they do all the tidal testing of the turbines. And because the interconnector is so bad back to Scotland, they wanted more and more tidal turbine testing being done. But they needed a use for the electricity because they couldn't get rid of it to Scotland. So they stuck an electrolyser on it, effectively just for the tidal turbine testing. So then they were over-generating hydrogen, obviously. So we get it shipped in, and so obviously the drawing, well, the photograph down the bottom right, that's a nanosun container. That's what the hydrogen comes in. So it comes in pressurised tube trailers. It actually comes in on the passenger ferry. They just don't tell people on the ferry that there's a pressurised tube trailer full of hydrogen on it. But yeah, it's a nice, simple project. It's a sod to get to, but it's a great looking project. I mean, Guy Martin was there with Channel 4 about 6 months ago. So once again, great when you get free publicity on Channel 4. The other great thing, because once again I said hydrogen's got great advantages, because it's such a clean fuel, it runs really, really sweet. I mean, for us, years ago we used to, the service maintenance on an engine used to be 1,000 hours, and it's always based on the spark plug life. Spark plugs now last 4,000 hours. So our service intervals now are based on when we have to change the oil, which is roughly every 2,000 hours. Because hydrogen's got no carbon content in it, the oil stays cleaner. So the service interval gets longer. So the idea we're working on now is to try and get the oil change back up to 4,000 hours that we do on the spark plug. Once again, that increases the operational availability. It makes it cheaper to run it because obviously you're not replacing oil all the time. So as I said, for us, that's why I said hydrogen's got an awful lot of advantages to it. Rather than obviously just the carbon thing, it's because it's a pure, clean gas. So once again, it's for us, we love it. So this is the problem, cost, and there isn't any. So everything comes down to cash at the end of the day. So at the moment, levelised cost of hydrogen based on S&P is about 12p a kilowatt. Which at the moment, compared to some people paying 6p at the moment for gas, normal gas, it's not too bad, but it's still economic death. But once again, it's going to come down with obviously subsidies. I mean, obviously over in America at the moment now, they've got $3 a kilogram subsidy. which once again is trying to levelise the cost down to $1 a kilogram, which is 1.8p a kilowatt. The European Green Investment Bank, or the European Hydrogen Investment Bank, is trying to do the €3 subsidy as well on it, with the idea of trying to bring it down to €1 a kilogram. But once again, we had the CFDs. We might be giving people threepence. So our subsidies are actually rubbish compared to obviously what the rest of the world's running. The Dutch have done theirs based on obviously carbon abatement. So they gave 1,980 quid a tonne on CO2 abatement from hydrogen, which really, really changes things. So once again, I said, this is the big problem. I mean, I said, if it was the same cost and you could get it as natural gas, every single one of our customers would switch instantly tomorrow. The problem is, you can't get it, and if you can get it, it's too expensive. That is the be-all and end-all of the problem. Getting it, the price. And I said, at the moment in the UK, we're getting left behind. The rest of the world's subsidising it to death. I mean, I said, the Japanese are just running away with this. We are getting left behind. But luckily enough, I said, we sell these engines all over the world. And I said, we ain't the best customer for these engines at the moment. But that is the crux of this matter. We can't get the bloody stuff, and it's too expensive when you can get it. But once again, I said, there's going to become a point in time when it's going to be right, when obviously the economics will work to switch it over. And I said, given the fact that the engines will last 15 years, we know at some point over that 15 years, the economy is going to change. I mean, at the end of the day, I mean, if the Europeans start producing it at the price they want, there's gas pipes from Europe, they'll just ship it that way. So if we don't start pulling our finger out and incentivising it to obviously get hydrogen generation in the UK, we'll just end up importing the European hydrogen. Or so you've got the Middle East, obviously at the moment now, they're gearing up obviously to import ammonia, because obviously it's easier. All the marine engine companies now are all designing their marine propulsion engines to work on ammonia, because obviously transporting ammonia is the greatest thing ever. So obviously it's got ultra high energy density. The big thing we've got a problem in the UK at the moment, we're lacking in nitrogen, obviously fertiliser. Ammonia is the answer for everything. I mean, it's what a lot of the work we're doing, obviously, with Centrica. Obviously, you import the nitrogen, the ammonia, you split it back down into the two things you want, hydrogen, nitrogen. And I said the Middle East is gearing up for that. I said, we are getting left behind. So once again, I said, if we don't start making it in the UK, we're just going to end up importing it from other people who are doing it cheaply. CO2 reductions, this is the other thing as well that people get confused about. So people think, well, if we get our gas grid to 20% hydrogen, that means we get 20% carbon reduction. Well, we don't, because obviously the different energy densities compared to hydrogen compared to natural gas, because said hydrogen's only got a third of the energy content. A pint of hydrogen's not worth the same as a pint of natural gas. So if we get to 20% hydrogen blend in the gas grid, it's only 8% carbon reduction. It's not until you start getting into the higher percentages, 80, 90, 100%, when you start really getting the CO2 benefit. But the amount of people think, well, it doesn't matter. If we get 20% in the gas grid, there's 20% of my carbon problem disappeared. You go, no, it's 8% carbon reduction. But once again, we're really realistic. We tell people the truth. This is the truth. 20% hydrogen is only giving you an 8% carbon reduction. This can be proved in anything you well want. So, the main conclusion really is purity. So obviously a lot of the big sort of our competitors in a certain way is obviously the fuel cells. Fuel cells need the 5 nines purity. You need 99.999% purity of hydrogen. To get that out of an electrolyser, you effectively need the cryogenic unit on the back end. Obviously to get all the high ends, the high purity. Our engines don't care. We don't care about the purity. We can run with gas impurities. It's an engine. It's designed to run with nasty things. So, because we don't need high purity, standard electrolyser without all the fancy stuff on the end of it produces 97% purity. Perfect for us. We can take hydrogen as a byproduct from the chemical industry. Perfect. As long as it hasn't got siloxanes or things like that in it. Simple. So this is the massive advantage of engines. We can take, obviously, impurities. But also as well, engines. It's designed to go up and down. We do load following. It's not a problem. Fuel cells, it wants a full, constant load, day in, day out. It doesn't want to fluctuate, otherwise the cells crack. So once again, there's an awful lot of reasons why engines are better than fuel cells. At the moment, I mean, sometimes, obviously, if some of my mates work in Bosch and they reckon they're going to crack the 99 purity thing and obviously get it working with impurities. But at the moment, that's not the situation. At the moment, they need 5.9 purities. And even, yes, and even gas networks, if you got to a complete gas network, once it comes out the pipe, it ain't still at 99.999% purity. It's picked up something nasty along the way. Engines don't care. And once again, virtual power plants with the island moding. It's a bog standard engine. I said, it's just a different gas. So that's it. Simple. Not hard, is it? And I said, it's nothing different. It's an internal combustion engine that we've made run on hydrogen. So the problem is getting the hydrogen. There you go. Simple.